We now talk about sequential circuits. The name sequential comes from a sequence of operations. So, for example, so if we need to perform um, 1 plus 2 plus then up to 100, or actually 1000s, or even more, or million or on billion, okay? So this is a very huge number. And so how do we do it in C++? So we use the concept of loop. So we actually cannot perform this all the operations individually. So instead we write a loop. And it's something similar. So when we need to do a sequence of operations, then instead of designing a combinational circuit, we design a sequential circuit. And so how it is designed, every sequential circuit has a combinational part, combinational block. So it has input, it has output, and also it has the memory elements. Present state and the next state. So how it works is that, so yeah, so like let's consider, so we need to do 99 additions. If we consider adding 1 plus 2 plus up to 100, so 99 additions. The result of the first addition is saved in memory elements. The memories are used for storing. Then the second input, then the next input is added with the storage number. Then in the next step, the result is stored again, and that's how. So when 99 operations are performed, then we can actually get the ultimate result from the output or from the next state. So however we design the circuit. So there are two types of sequential circuits. Synchronous sequential circuit. Let's write them. Synchronous, and it has a common clock pulse. What is a clock pulse? We'll talk about it later. And the second type is asynchronous. It doesn't have a common clock pulse. In the sequential circuits, the memory elements are formed by the latches. Latches have some limitations. That's why the flip-flops we use instead of latches. Then in sequential circuit design, we have the concept of state table and state diagram. So what is a state table? So we are familiar with the truth table. A truth table has input and the corresponding output. That's a truth table. Now, so for the sequential circuits, we have present state, and we have input. On the other hand, so we have next state, we have the output. This is we call a state table. And another graphical representation of the state tables is a state diagram. It's just two different representations of the same information. Sometimes state diagrams are easier to follow, easier to understand because they are diagram. Now, so what we do in sequential circuit design, so we first study latches. First, we study S R latches, then S prime R prime latches, then S R latches with control input, then D latches. And after we finish latches, we'll study flip-flop, then we'll study how to design sequential circuits. We study counters, we study registers. So in this lecture, our goal is to finish the latches. And so let's start with the SR latch. Well, so before starting the SR latches, I also need to talk about the latches. The latches are the devices, are the digital devices which we use to store information. In this case, information are the bits 0 or 1. So one latch can store 1 bit. One latch can store 1 bit. So now let's start the SR latch. So we want to draw a very particular type of circuit. Then we want to analyze this. Let's consider this one is Q and that one is Q prime. We have S at the bottom and R at the top. But now this Q is also connected to the second NOR gate, and then this Q prime is connected to the first NOR gate. To the first NOR gate. And I also need to mention that this S stands for set, and the R stands for reset. So in this case, it is possible that Q prime maybe 0 0 0 1 1 0 1 1. So these 4 possible combinations. So if Q prime, if they are 0 0, then you see here, if Q is 0, then Q prime is also 0. So this is an undefined state, something that we do not want in our design. Then 0 1, we call it a reset state. Then 1 0, we call it set state. 1 1 is again undefined. Now let's analyze the functionality of this circuit, this small device, by using a function table. So we analyze by using the table, and this table we call the function table. So it has Q, the present state, Q prime, it has S, it has R, then it has Q plus 1, q prime t plus 1. So for each combination we want to analyze. So it's possible that q is 0, qt is 0, and q prime is 1, then sr 0 0 0 1 1 0 1 1. So 0 1 0 1 0 1. Then that's possible that q is 1, q prime is 0. Okay, so this 8 possible combinations we will analyze. Okay, let's start with the first combination. So we have q0, and q prime 1. Then we have s0, r is also 0. So s is 0, r is also 0. So now if q is 0, this way, and the s is also 0, then the output of the OR gate will be 0. Then this is 1. Q prime is 1. Then q prime is 1. Then output of the OR gate is 1. Then the output of the NOR gate is 0. So 0. So this is not changing. So for the first combination, it still is the same. For the second combination, so what we have? We have 0 1, the q prime, and the s is 0 and r is 1. So what happens if this r is 1? So now q and s makes it here 1 and 1 makes it here 1 0. It's still not changing. It's still 0 1. Then for the next combination, we have S1 R0. S is 1 and R is 0. So 0 and 1 will make it 0. 0. 0 and 1 will make that 0. So that's 0 0. The state is 0 0. So now if both are 1, all, so let's analyze it for the previous combination again. So what we have actually here, we have q0 and q prime 1, we have s1 and r0. So now 0 and 1 will make 1 0, will change it to 0. Then 0 and 0 will change it to 1. 1 and 1 unchanged, 0 and 0 1. So this is 1 0. This is actually 1 0. This is 1 0. Now we have S1 so what do we have? We have q0, q prime 1. We have s1, r is also 1. So we have 0 1, we'll make it 0 0, 0 1, make it 0 0 1 0 0 1. Okay, so now both are 0. Then so what do we have? We have q1 and q prime 0. Now we have the inputs s and r 0 0, so both are 0. So on 0 we'll make it 0 0 0 1, so it's 1 0, it's on 0. Now again for 0 1, now r is 1, so 1 0 will make it 1 0 0 1 will make it 0 1. Q is 1, q is 1, and q prime is 0, and s is 0, r is 1, s is 0, r is 1. So this 1 and 0 will make it 0 here. This 0 and 1 will make 0 there. 0 and 0 will make 1 here. 1 and 1 will make 0 here. So it's actually 0 1. It will be 0 1. Similarly, if we have q one and q prime 0, and s is 1 and r is 0, so then 1 and 1 is 1 0, this is okay. 0 and 0 0 1, okay, so it's on 0, it is now on 0. So how about now? So if we have on 0 and s is 1 and r is also 1, so 1 1 will make it 1 1 1 will make it 1 0 0 1 0 1 will make it 0 0 1 will make it 0. So okay, so now we got here actually 0 0. So now if we try to summarize this function table, so how do we find? So when SR, when SR 0 0, what happens? Where is SR 0 0? There is on combination, there is on another combination. So when SR 0 0, then Q 0 1, Q 0 1, Q on 0, Q on 0, so it's no change. Then how about for SR 0 1? So what do we have? 0 1, then it's 0 1, 0 1 0 1, so it's 0 1, Q prime 0 1. So if 0 1, it is a reset. Then for 1 0, if 1 0 here, 1 0 there, so it's 1 0 is set. Then if it is 1 1 1 1, then 0 0 0 0, it means it's undefined state. So the limitation of this latch is that it's undefined. There is an undefined state. So when s is 1 and r is also 1, then the state is undefined. So now, so in this case, if we have s 1 and r 0, and the power is 1 in this circuit forever, then q will be 1 forever. Similarly, if we have S0 R1, then Q will be 0 forever. That's how, by using this small device, we can store a single bit. The symbol of this simple device is that, so this is a block. We have S, we have R, we have Q, we have Q primes, Q prime. So now we study the second latch, S prime, R prime latch. Instead of using a NOR gate, we are going to use now a NAND gate. We have two NAND gates. We have Q prime, we have S prime, R prime. Now we want to analyze the function table in this case. So we have QT, we have Q prime T, we have S prime, we have R prime, then we have Q T plus 1, Q T plus 1, Q prime T plus 1. And similarly we will have 8 combinations, and we want to analyze for each of the combinations. 0 0 0 1 1 0 1 1 0 1 0 1 0 1 0 1 1 0 1 0 1 0 1 0 0 0 0 1 1 0 1 1. If Q is 0 and Q prime is 1 and S prime and R prime both are 0, then what do we get? So this 0 and 0 will give us 0 and 1. This 0 and 1 will give us 0, and that is also 1. Okay, so this will be 1 1. This is similar. If we do this combination for this, will also be 1 1. For these two combinations, the state is undefined. Then so if we have Q 0 and Q prime 1, so we have this 0 and that is 1, and we have S prime 0 and R prime 1. So now this 0 1 will give us 0 1, and 1 0 will give us 0 1. 1 1 will give us 1 0. 0 0 will give us 0 1. So that's actually 1 0. Similarly, for the third combination, so we'll find it, so if we go through the process, similarly we'll find it it's 0 1. So how about if S prime is 1 and R prime is also 1, and we have this Q 0 and Q prime 1, then 0 and 1 will give us 1, 1 and 0 will give us 1, 1 and 1 0, 0 and 0 1. So it will be 1 0 1 0 1 0. Am I correct or not? Let's analyze this. So little more detail. So what do we have here? For the fourth combination, we have Q 0, Q prime 1, we have S prime 1, R prime 1. Now, so we can start with the first NAND gate or the second NAND gate. It doesn't matter. The order doesn't matter. So let's start with the first NAND gate. So we have, or the second NAND gate, doesn't matter. So 0 and 1 for the second NAND gate. 0 and 1 will give us 0 1. This 1 is unchanged. This 1 and that 1 will give us 0, again unchanged. So 0 and 1 1, 1 and 1 0. So this means that is still 0 1. Similarly, so when it's 1 1, we get 1 0. So for the fifth combination, we'll get 1 0. The sixth combination will have 0 1. So I haven't gone detail for each of the combination. So what is the summary for S prime, R prime? So what happens if s prime and r prime are 0 0 0 1 1 0 1 1? S prime r prime, they are 0 0. So s is 0 0 0 0. So when they are 0 0, then it is undefined. When s prime r prime are 0 1, then it's set state. 0 1 set state. It is set state. So when 1 0, reset state, 1 0 reset state. For 1 1, 0 1 0 1 0, 0 1 0 1. So it's unchanged. That's the functionality of this latch, and by using this device again, so we can store a single bit. But again, the limitation is that one state here is undefined. When s prime is 0 and r prime is 0, then the state is undefined. That's something that we don't want. So now we draw the symbol for this device. The symbol is simple. So we have s prime, we have r prime, we have q, we have q prime. That's the symbol. We now study the SR latch with the control input. The total 4 NAND gates we have here is for C. That's S. This R. And we want to analyze the functionality of the circuit. So when C is 0, what happens in this case? When C is 0, the control input is 0, then the output of both of the NAND gates is 1. So it means that if we consider S prime R prime latch, this part is the S prime R prime latch, and S prime and R prime, so both are 1. If both are 1, then it never changes, the state never changes. So if C equals 0, if C equals 0, then no changes occur. It means that by using this C, so we can control the functionality of this latch. That's why it is called the control input. So when C equals 1, what happens? So it happens when C equals 1, then we get if S R, if S are 0 0, then S prime R prime, they are 1 1. So if they are 1 1, then no change occurs. No change occurs. And if 0 1, S is 0, R is 1, then S prime is 1 and R prime is 0. So then it is reset state. Similarly for 1 0, so when S is 1 and R is 0, then S prime is 0, R prime is 1. So then it will give us the set state. So when they are 1 1, then S prime is 0, R prime is 0, and this will give us an undefined state. So if you see the functionality of this latch is exactly the SR. So we built the SR latch previously by using NOR gates. Now this time, so we built the SR latch by using uh, previously we built by using NOR gates, now by using NAND gates, but the functionalities are the same. The additional feature in this case we have is the control input. The symbol for this latch is, it has S, it has R, it also has a control C, and it has Q, it has Q prime. Now we study the very last latch, and we call it is D latch, D for data. First we draw the SR latch with control unit. We have the NAND gate. We have two more NAND gates. Q prime. Is the control input. Now, so if you can remember, this is exactly the SR latch that we have studied previously. Yes, S prime, R prime. So the limitation that this latch has is that it produces undefined state. It produces undefined state. Now, so what can we do? See, in order to overcome the limitation, and we also saw that when S is 1 and R is 1, then it produces undefined state. So now, if we do something here, like, so we use an inverter. We use an inverter here, and then we connect these two. Now this new input is now D for data. Now if D is 0, then D prime is 1. So if D is 0, D prime is 1. If D is 1, D prime is 0. So there will never be the case that S and R both are 1. So now if we want to analyze this one, so what happens? Okay, so if we have D, so D might be 0, D might be 1. So when D is 0, let's put here 0, and then D prime is 1. This means that S prime is 1 and R prime is 0. So if S prime is 1, then R prime is 0, then it is a reset state. In reset state, the Q is 0 in reset state. So similarly, when D is 1, then D prime is 0. 1 0, so S is 0, S prime is 0, and R prime is 1, and it is set state. In set state, QT plus 1 Q is actually 1. So in this case, so whatever the bit we have in D, it may be 0 or 1, the same bit we also get in Q. So if we store a bit 0 in D, and then this bit goes to Q, and as long as there is power in this circuit, this bit will be stored forever. So we can use this device for storing a single bit 0 or 1, and also important that it doesn't have any undefined state. Thank you so much.